All right, so thank you so much for joining us today. My name is Leela Nordman, and I'm the STEM Lab Director here at the Fairbanks Museum and Planetarium. And today we have Hannah Buckner, our AmeriCorps, talking about the lifespan of a star. For those of you who are joining us through Zoom, please feel free to mouse down and use the chat function or the Q&A function. I'll have both of those open and pass your questions along to Hannah. If you are joining us through YouTube, please use the chat function there. And again, I will see those questions and be able to pass them on to Hannah. So thank you so much for joining us, and I'm going to go ahead and turn the class over to Hannah. Thanks again.
Okay, great. Well, thank you everybody for joining today. It is going to be a fun morning. We're going to be talking about stars and their lifespan, and from birth to their death, or even their rebirth. So let's get started. So I'm going to pull up this slide so that we can see it. And great. So welcome to this class, and if you have any questions, again, please let Leela know, and she will be happy to get your questions asked, or if you would like to answer them live, just raise your hand and she can help you do that. So first off, let's start with what are stars. They are pretty recognizable to the general public. They're also one of the most known astronomical objects in the universe. They represent actually quite a fundamental building block of galaxies and space as we know it. The ability to know what kind of star we're looking at, we can tell that by age, how many of them, where are they, and what they're made of can really tell us a story about kind of just how that star came to be in its lifetime and where it is in its solar system, if there is planets or not. But it can also tell us how that formed and how the other parts of that system formed as well. So stars are usually balls of burning hydrogen gas that are burning through a process called nuclear fusion. So that essentially is just subatomic particles that are hitting together and creating energy. And it's very explosive. We can somewhat do it here on Earth. They create tiny little balls of light or stars in their particle colliders. So we have created stars on Earth, but they're not to the same size and recognizable distinctions of a normal star as we would categorize them. So what we're going to mainly be talking about today are main sequence stars, which are just a large portion of the stars that we have now. We are calling them main sequence because it is actually the phase of a star's life that dictate that they are either just born like a baby and they're growing up through their teenagehood and they're reaching adulthood. So I guess if I was a star, I would be just entering into the adult phase and I'd be reaching the end of my main sequence stage as I would be getting closer to being an elder or possibly dying. Whatever, that's sad. We're not thinking about that.
And Hannah, we have a question which you may be in the process of answering, but someone was asking how big is a star, and it sounds like there's a whole process.
So maybe that's actually a complicated answer. So I'm not going to answer it right now. because we are going to be talking about that in just a minute. But thank you for jumping ahead of the
Great, thanks.
class. Okay, so yeah, so we said that stars are balls of burning hydrogen gas, and the hydrogen part is very essential. When we look at a star, there is a field of science called, well, not a field, but aspects of physics, chemistry, and astronomy called spectroscopy. And that tells us by looking at light and the colors that we see in return, it can tell us what an object or gas is made of. So when we look at stars and we see how much hydrogen we have, we can also kind of tell how late they are in their lifespan. A star that's in main sequence will have majority hydrogen gas, and as it keeps burning its gas, it will actually form new elements. And if you're not really sure what an element is, they are the foundations of actually matter. They are composed of subatomic particles called protons, neutrons, and electrons. And based on how they're built, and they get thicker, they can get heavier, and those form different elements like carbon, oxygen, which we need to breathe, nitrogen, even gold, iron. All of those are elements. And so as stars keep burning their fuel, they will get less and less hydrogen, but they'll be forming things like helium, carbon, nitrogen, oxygen. Sometimes they'll eventually form gold, but those are in certain situations, or iron. And when you get to iron, it can get pretty dangerous. So we'll talk about that when we get there. So what kinds of stars are there? Like I said, we will be talking about majority main sequence stars, but also be able to touch on other types of stars once we reach that point. Oh shoot, sorry. I was hoping, here we go. So these are called main sequence stars right here. We measure them in terms of their spectral type, so that kind of just helps us be able to categorize stars that are like each other. So looking at an O-type, and we'll go a little bit more deep into like O, B, and A in a minute, but looking at this O-type, you can see that we list the spectral type, the temperature, the size of the star, the heaviness or the mass of the star, the brightness of the star, which is also called luminosity, and how long it'll actually live. And then lastly, the abundance is the amount of stars that actually exist in the universe. So when it lists that an O-type star has an abundance of 0.00001%, it means that they're really rare in the universe. And in the makeup of stars, they're really not that common. And I can get back to that in a second. But so yeah, we have our main sequence stars here, and I'll be able to go over them a little bit later. But we also have stars like giant stars. I'll also be able to go over those more later in detail, but I think this chart is really cool because it does show you stars in respect to our stars. So it makes you be able to comprehend, to understand in a digestible way how big these things are and what they might look like to us. So actually, this yellow dot is our sun. Our sun is a G-type main sequence star. It's about halfway through its lifespan. And because we have grown up with this star, we have used it as a reference point for the rest of space. So when we're looking at a K or M star, we know that they are stars that are smaller than our sun, and they have less weight. Well, not weight, they have less mass. But when we look at stars like giant stars, they are incredibly massive. But they're not as big as supergiant stars, which are supergiant. They are the most massive, but funny enough, they are not the least occurrent, meaning that they aren't the most rare. So it's actually pretty cool to be able to see this. And then lastly, we have white dwarfs that are very small. This dot actually, if my cursor can get there, it is about the size of Earth. So you can actually see how big our planet is in terms of our sun too, because you have a white dwarf that is the size of Earth, and then we have a G-type star, which is our star. So we'll get to main sequence stars in a second. So how do we measure and categorize stars? So like I was saying before, we look at stars in terms of color, temperature, well, their surface temperature, their spectral class, and their brightness and their absolute magnitude. So in terms of things that everybody can understand, we'll talk about this first. So these graphs are called Hertzsprung-Russell diagrams, also known as HR diagrams for short. And they can really show us if we're looking at a star and we're not really sure about like what kind of star it is, we can use this map to tell us aspects about it, because stars that are very similar to each other will have similar lifespans. So remember when I was talking about O-type stars and how they're really rare? Well, these stars up here where my cursor is, I know it's a little laggy, just bear with me. These are O-type stars. And they're very rare because they don't live that long. When we're looking at O-type, we're seeing that they have surface temperatures that are above 30,000 Kelvin, which is a scientific measurement of heat or lack thereof. And that can tell us, you know, how hot something is, but it's without using Fahrenheit or Celsius, which is either based on the boiling point of water or the temperature of the human body. So having Kelvin is a lot more just easier for conversion for scientists. It's pretty constant throughout. And then when we look at luminosity, we see that as we get to smaller and smaller stars, they're actually getting much dimmer in the main sequence. And then we also, if you hop on over to this graph, we'll see their color, which goes from blue to violet, but that's not pretty common to have on a graph, and then absolute magnitude, which is saying how big these stars actually are. And then these green lines here are telling us how long a star can live. So when we're talking about a star like an O-type star, the reason that they actually live so short is because they're so incredibly massive that they have all of this hydrogen fuel. And the way that they're burning their fuel is actually pretty crazy, because they are essentially having a feast day on all of their hydrogen fuel, and so they gobble it up so quickly that they end up dying because they have wasted their life rope on what is keeping them alive. Because as long as a star can burn hydrogen, it'll be a main sequence star. So when you have an O-type star, which I believe I have here, you can actually see, well, first you'll see that if you recognize constellations, you'll recognize this little 3-star line here. you'll actually figure out that this is the constellation Orion, and we have Betelgeuse here. I'll talk about that later because I know tons of people are curious about that. But if we go down here, we'll actually see a few bright stars. And there is a star here called Theta Orionis that is an O-type star. So what that tells us is that it's going to be bright, white, and blue, and it's going to be very hot. We know that because it's an O-type star and it has a luminosity class. We measure brightness in classes, and it's an O-type B. A star that's an O-type will have a mass that is 15 to 90 times greater than the sun. So it's very heavy. It's got a very intense amount of gravity. Like I said, it's very hot, between 30 and 50,000 Kelvin. They are 40,000 to 1,000,000 times more bright than the sun, which if you're outside and you can't even look up at the sun, you're gonna get blinded. These stars will blind you. Yes, Leela. Hang on, you're muted.
Thank you. Someone was asking why they are white, so on the spectrum there.
Great question. So you can actually figure this out too by looking at a candle. I would burn a candle right now, but I don't think that'd be very safe. So when you look at a candle, and you have fire, obviously it's a lit candle. The bottom of the fire is white and blue. And when you're looking at energy, physics, I love physics. When you look at the wavelength spectrum, which is how we measure light, light moves as waves sometimes. And when something has more energy, it has higher amplitude, which is the distance between the highest peak and zero. And that amplitude can go both positive and negative because it has wave-like motion. So when you're looking at the wavelengths, blue light has way more energy and has a very high amplitude, but when it's red or orange, it'll have a smaller amplitude and it'll be more drawn out. So and actually the energy is related to heat. So a star that has more energy or a higher temperature means that they're going to have a lot more energy in their wavelength. So because blue is actually way more based with energy, it has a higher frequency than red, we're going to see stars that have massive amounts of energy and heat, they're going to be blue. And stars that are kind of dying, or they don't have that much energy, or they're not really wasting their hydrogen fuel, they're going to be redder because they are not emitting so much energy. It's also why when we're looking at smoldering coals, after you've put out a fire, why they're still warm, but they're not emitting fire, they're actually like glowing red, is because they're cooler than what the fire was. Yeah.
And then there's just a second question. What is the biggest star that maybe we know of? Because it sounds like you're talking about very large stars here. Is there one that we can point to?
One that I can think of off the top of my head is Betelgeuse. It's not a main sequence star, but it is a supergiant and it's massive. And I'm pretty sure that a lot of people have heard now that Betelgeuse is expected to become a supernova, and we'll kind of talk about what that means later and like when we're expecting that. But it basically is saying that this star is super massive. It's reaching the end of a point of its evolutionary stage, or it's a part of its lifespan. And so it's about to explode, and then it's going to die in terms of stars. not actually going to die. But yeah, so Betelgeuse is very massive. I'll kind of explain how big it is when we get there, because I do want to talk about Betelgeuse at one point, but that's also a really good question. So as I was saying with O-type stars, because they're so massive and they go through their energy core very quickly, they live very short. So as we saw, their abundance was a fraction of the universe. They're so rare because they burn through it so quickly. In terms of stellar lifespan, we are going to think that this is so long, but in terms of space, this is actually quite short. O-type main sequence stars will typically spend less than 1 million years as a main sequence star. Our universe is about 14 billion years old. So in the grand scheme of things, they really just don't live that long. Another type is a B-type main sequence star. The star that we're looking at here is Phi Andromeda A. They're also very bright, and they are a spectral type B. Sorry, it's very early in the morning. Their mass is not that much more than the sun, because our sun it's right smack dab in the middle. B-type main sequence stars typically have a mass that is 2 to 16 times more than the sun. Let me go back to this so that you can actually see where we are. So here is where we are. They are they're very big. They have a temperature typically around 20,000 K. Their radius, like I said, is 3 to 5 times more, or 16 times more. No, that would be an O-type. They're pretty bright. They're about 1,000 times more than the sun, well, brighter than the sun, and they can live to be 100 million years, typically. They're much more abundant than O-type, but still not the commonplace star. And you can tell that as we're getting smaller and smaller, that it's getting slightly less blue. That's because it's moving towards yellow. Yeah, and then we have an A-type sequence star. So that would be here. A-type sequence stars have a surface temperature of about 8.5. They have about 8,500 Kelvin temperature, which is much closer to what our sun experiences. It's slightly bigger than our sun, 1.7 times greater, and it has a mass that is double the size of our sun. It's about 20 times brighter, and it can live for about 1,000 million years. So definitely, as you'll notice, as we're getting smaller, stars can live significantly longer, which is a great benefit to many stars. When we're looking at G-type stars, we are seeing our own sun. Well, sorry, I skipped F. Also important. They have a temperature of 6,500 Kelvin. They are still slightly greater in mass and radius than our sun. Again, radius is the size of the star. They are 4 times brighter than our sun, and they can live to be 300 million years old, and they're only about 2% of the universe. So for every 100 stars, there are 2 F-type stars. Our sun, what a beautiful sun. Our temperatures, sun-like temperatures can have about 5,700 Kelvin. Their radius, mass, and brightness will be very similar to what we have now. So we will If there's a planet that is orbiting a sun like ours, they will experience similar temperatures. Depending on where they are on the planet, they'll have some differences, but it can be pretty habitable if it's a living planet, if it's a planet we can live on. And our sun can live up to 10,000 million years. So our sun is actually, I'm sure plenty of people have heard that our sun is about 4.5 billion years and it can go up to 10 billion years. Our sun has gone through, it's possible that our sun has gone through a few iterations of a life cycle. And so it's just the new birth of a star that came through. So we've still got some time. Like I said, our star is a teenager, is at its teenage lifespan. It's actually quite dormant right now because it's not generating as much energy inside. No need to worry. It's just sleeping. Teenagers do that. It's going to have about 4.5 billion years to go. Going smaller, we have K-type stars, which have a lower temperature at 4,500 Kelvin. They are slightly smaller than our sun, but still bigger than our planet. And they have smaller mass and brightness, but they can live longer, significantly longer. And they compose 8% of the universe. So for every 100 stars, there's about 8. And then for M-type stars, they are very cold. They are 3,200 Kelvin. They are very small. They are just 0.3 radius in comparison to Earth, the sun's 1. They have much less mass and they are not bright at all, which is why they're red. They have less energy, so they're gonna be on the red spectrum, but they can live the longest. I can't even quantify how much it is, but they take up about 80% of the universe. So.
And we had a question that's sort of related to that. It sounds like M stars are the oldest stars. Is there an example? Someone is asking, what is the oldest star?
Ooh, I don't know that off the top of my head, but I can certainly get back to them. It's also a very Googleable question, but there's a lot of stars out there. I would imagine M-type stars probably formed towards the beginning of the universe and are still kicking. Yeah, like I said, they're very abundant. They've been around. They're typically pretty old. That's all I can say on that.
Okay, great. Thank you.
Yeah. So yeah, those were our main sequence stars. We had A, F, G, K, and M. So now we've reached kind of the end of adulthood. So once you've reached your prime, you don't dwindle, but you experience just changes in your life, whether it's bodily, mentally, physically. You are bound to change as you reach the end of your life. So what happens after a star becomes an adult? It really just depends. So you heard me mention all of these stars that have a very wide range of size. That size can really just dictate what comes next. So as you see here in the middle, there's a star forming nebula. So we know that stars form by gas and dust that are in these nebulas. They begin to collect and condense, and they get very, very close and tight. And so then, because they're so tight, they begin to warm up, and they start to experience nuclear fusion, which is they're starting to burn hydrogen, and they can continue to get bigger, and the remnants of their gas and dust and other matter can form planetary systems, which is what we have right now with our sun and our solar system, and that forms a protostar, and that star becomes either a sun-like star or a massive star. And depending on that kind of star type, it will dictate what the possible outcome is. And so for a star like ours, we see that it's actually going to become a red giant. And a red giant is pretty massive. Let me go back to that slide about where giants are. So you'll see that stars are typically like our own, will become giants when they reach the end of their life. They kind of go up in this area and become giants. So we are seeing stars like Aldebaran or Pollux and Arcturus. Those are pretty recognizable stars in the sky. They have become giants, but Aldebaran is more of a red giant because it has that classification of it. So these stars are not remnants, but they are stars that have moved out of their prime, their main sequence, and are starting to enter into this new phase of life. And so when stars that are going through this evolutionary phase, they'll keep burning the rest of their fuel before they can no longer keep up their energy. So the reason that stars can get so big is because they have the energy to keep holding up the gravity of their surface. So when a star no longer has the energy to keep going, it'll actually collapse and then come back out. And so with red giants, we're seeing planetary nebulas. Let me see if I can pull these up. Yes.
And we just had a quick question, because I know you've been talking about the colors of stars and everything. And someone asked, is it possible that there's ever been a green star? Is that in the color spectrum or the or I'm not going to be able to say it either.
the spectroscopy.
Yes, thank you.
I don't think so. I know that a large majority of stars, at least to the eye, I don't believe they will appear green. We do know that our sun, when you look at it through a specific wavelength of light, I can't remember if it's infrared or if it's gamma or something else, but the sun actually does appear green. And NASA posts pictures, I believe, on St. Patrick's Day sometimes of the sun as it appears green. So you won't necessarily see a green star. I think because if a star appears green, it might be because it has iron. And when a star has a lot of iron, it's going to collapse. So actually you see that not with giants, but white dwarfs. But I'll get to that in a second. I want to talk about
Thank you.
yeah, I want to talk about planetary nebulas. So I want to clear up any confusion with these stars. They're not really stars. They don't have planets. It's just that the nebulas have emitted gas, and we have a stellar remnant that's in the middle that looks like a planet. And the gas is expanding, it's glowing. The gas is ionized, meaning that electrons have been taken away. This is also called electron degeneracy, for those of you who are chemically inclined. So these stars have come from red giants who have imploded and have reached the end of that life phase. And the example you're seeing here is actually NGC 6326. It's very beautiful. These nebulas are a beautiful way of showing stellar death. Because of the colors that you're seeing, it actually can show you what was in the star. The redness are clouds that are being blown away. So you're not actually seeing just like stagnant or staying still gas. You're seeing winds that are blowing away gas. And because there is wind, eventually all of this gas is going to disappear and you're going to have a remnant, which leaves a white dwarf. And white dwarfs are stellar core remnants that are made up of, like I said, an ionized matter, which is without electrons, so it's going to be called electron degenerate. They are the size, no, they are the mass of the sun. They have the density of the sun, which is a lot. It's very heavy, but it's the size of the Earth. So that means that the material is actually quite heavy and can rip up matter. So you're actually, the example I have here is Sirius B. So when you're looking at Sirius in the sky, it's actually a binary system, which means there's two stars. So this is Sirius A, this is Sirius B. And Sirius B is very small, as we talked about. But if I was actually telling Leila this before, if you take about a tablespoon of white dwarf matter and you put it on the Earth, maybe it's a neutron star. One of these stars, you take a tablespoon of this matter and it'll actually create a hole in the Earth, and it'll go straight through the through the center of the Earth. And the other one, if you put it even near the Earth will actually collapse and get sucked into the surface of the sun because the gravity is so strong. So just reviewing that again, for a star that forms like our sun, they go through the normal protostar phase, and it goes through its main sequence phase, and it can last a very long time. But as it reaches the end of its life, it expands and it becomes a red giant or another type of giant. And then as it reaches that end of its phase and stops burning any sort of fuel, it will go in and then out and form planetary nebula, which will eventually blow away into a white dwarf. But there's also the chance that the planetary nebula will become a star-forming nebula, which means it can give life to more stars. And that has any option of building stars of any size. It just depends on the conditions. There are other types of stars that form. And these get a lot of attention because they are spectacular events. And there's 3 outcomes that can happen, which are very exciting.
We do.
Yes. Sirius B is a part of Sirius A. Okay. Well, they're not part of Sirius A, but they're very similar. Yes, Leila.
Thank you.
Okay, so let's say you're not a sun-like star, but you're actually a massive star. Those stars are very dramatic. They have all the flair of a diva, and they expect to go out like one as well. So we talked about these supermassive stars that we have O-type, B-type, A-type. They are big, they are hot. And when they reach the end of their lives, they become a red supergiant. So literally just a bigger version of a red giant. And you can see, why isn't this going? Great. What? Oh, there we go. I just had to click on it. So when we're looking at the difference between giants and supergiants, it's about the order of magnitude. So we have giants that are about here, and then they can be brighter. It doesn't really matter. And then we have supergiants, which are much bigger than supergiants. So when a massive star becomes a supergiant, it expands out just like our sun would eventually into a red giant. It just gets really, really big. And then experience the same core collapse as a red giant does with the planetary nebula, except these stars are so massive and they have so much mass that when they collapse, it causes a massive explosion, and it goes, and they emit much gas, and they are very bright. But unlike planetary nebulas, which can last for a very long time in terms of human understanding, supernovas are actually, they don't last that long. They could last maybe for a few days, maybe a few weeks, and but they slowly get not bright. They lose their brightness. They become very dim. So when we talk about things like Betelgeuse exploding and everyone's looking out for it, it's because if they miss the first explosion, they're going to miss the brightness of the star going up and then falling down. They'll get like the latter half of it. And everybody wants that first big bang, pun intended. And so let's see. So a supernova, like I said, is a powerful and bright stellar explosion. And it occurs when a star reaches the end of its stage, or actually it can happen with white dwarfs, but that is a astronomy thing that I could talk about for hours, and we don't have that kind of time. So the example you're seeing here is actually a supernova remnant, SNRE 0519, and it's in the Large Magellanic Cloud, which is pretty cool. I think it looks nice. And so from a supernova, there are three options. It can become a star-forming nebula, just like a planetary nebula can. Or it can become a neutron star. And remember when I was saying that there was two options of something that could create a collapse in Earth, or it can suck Earth into its surface. So the neutron star was the other star. And these are really cool. I saw this diagram of what a star looks like, and thought it was pretty cool. You don't necessarily need to understand what it is, but it kind of just shows the size of a neutron star. So we actually see that the outside is made up of all of these neutrons and electrons, and it's all ionized. And inside there's like these theoretical plasma, and all these like numbers that you're seeing have to do with density. Not going to go into that, don't worry. But essentially what I'm saying is that it's also the remnant of a collapsed core of a giant star, just like a white dwarf would be, except it's only for solar masses that, no, it's only for total masses of stars that had a mass that was between 10 and 29 solar masses, meaning the mass was 10 to 29 times greater than that of our sun. So they're massive. But because they're a collapsed core, they're also very small. So after these great stars have collapsed, they remain these very small but incredibly dense stars. They don't really generate heat. All they have is the heat from their explosion, but then they start to cool over time, and they can be red or white, or it just depends on like the heat at the time. And then they just stay there. But the other option is that the supernova can become a black hole, which is when all the mass in a certain object collapses to a certain point that it just starts to, the gravity of itself starts to just inwardly collapse, and it just keeps falling in. And so we know that there's a black hole at the center of our galaxy in Sagittarius A. Some solar masses, trying to think, I think it's if the sun were to collapse into the size of a grapefruit, it would become a black hole. Or that could have been Earth. One of them, if it collapses into a grapefruit size, it'll have that much gravity where it'll start to just suck everything in. But you can also get black holes actually from neutron stars that collide, kind of like pulsars, which are pulsating neutron stars. There's so many other stars actually, but there's just so many to go over. I thought I'd focus on the main ones. So yes, what we've seen from supermassive stars is that they form from as a protostar. They just are bigger. They have a lot more hydrogen that they can burn, and they eventually expand, and then they collapse, and they can have three ways of going. They can become a star-forming nebula, they can be a neutron star, or they can be a black hole. And we don't really know what happens after black holes. There's an idea that after all the stars die away, because eventually they will, all that will be left is a black hole area, a black hole time, and that's called the dark era in theory. So beyond that, we don't really know what happens next, but that's what we would like to figure out. And so one day I hope to be able to figure out more about black holes and what goes in them and what happens after that. Yeah, and that was the lifespan of stars. Does anybody have any questions that weren't answered?
It looks like you've answered the ones that came through as we were going, but yes, feel free if anyone wants to right now ask any questions about the lifespan of a star, please do. We can also always answer them later if you come up with questions. It's great. You can email Hannah or myself, and also just doing anything through Facebook for help with identifying anything that you're seeing at night. That's another way that Hannah can get back in touch with you. And it looks like folks have just said, thank you so much for your class. So yeah, if there's any last words you want to share out, feel free. Otherwise, thank you all again for all your effort and everything here, Hannah, doing this class.
Yeah, it's my pleasure. And I'm happy to share my love of the stars and anything else about them. So if anybody has any questions, please feel free to reach out to me by email. If you don't have it, I can say it right now if I can remember my email.
Here, I can put it in the for
I believe it is Buckner at
yes. At fairbanksmuseum.org.
At fairbanksmuseum.org. Again, I'd be very happy to answer any questions about stars, anything else you have about that. Regarding Betelgeuse, I just realized I never talked about what's going to happen. We don't know when it's going to explode. It could be very soon. It could not be. It's going to take about 600 years for it to get here. So it could have already exploded, but we still haven't had the light reach us yet. Because when we look back at stars, we are seeing light as it was a certain time ago, because stars that are certain distances, it takes that amount of time for the light to reach us. So when we look at the sun, we're seeing the light in the sun as it was 8 minutes ago. So we don't know.
Someone was saying how far away. So I guess how far away is Betelgeuse? You may have just said that though.
Yeah, it's about 639 light years away, which, I don't know that off the top of my head, just because it's a pretty massive number. It's many millions of miles away. So
it sounds like there's some great stuff because for people to do a little of their own research on too, with some of their own questions. Yeah.
Yeah, and it's really good too to also practice your math.
Yeah.
It's actually pretty easy math. People get pretty daunted by it. I think it's pretty easy. If you need help with your math, feel free to reach out.
Well, great. Thank you so much, Hannah. This is a wonderful experience to get to learn more about the lifespan of a star. And please look online for our additional classes this week. Our next class today at 11 a.m. will be Geometry and Nature, geared towards 3 through 5th grade. But again, that will be both on Zoom, which you can find on our virtual learning page where to click through to be on the Zoom call or video with us. And then also, again, through YouTube, feeling free to watch the class and or ask questions in the chat box there. But thank you again. And we'll go ahead and finish up here. So I'm going to end the meeting. Thanks again.